So welcome to the last chapter of this course, chapter 5, which is titled Quantum Physics in 3D. And there are essentially three main items at the menu. One is the description of material point in 3D. We are going to see that this is essentially what you expect, the obvious extension of the theory of material point in 1D to 3D. So that's not particularly difficult. But then there will be a big chapter on a very important object, which is angular momentum, that is not only for material points, angular momentum in general. Angular momentum. This is associated with rotations. Okay, rotations is something we could not speak of in 1D for obvious reasons. Now we are going to be able to speak of rotations, and you know that in 3D, contrary to 2D, rotations do not commute in general, right? As soon as they are not around the same axis, they don't commute. So that there will be a whole structure here of algebra to be studied. In this chapter, there will be two examples. One is a spin half, revisited, the same as we did in the two-level system, but now revisited as an angular momentum, and two, the orbital angular momentum, which is L equal x cross p, the same object as you saw in classical mechanics. And then, with the knowledge of the orbital angular momentum, the last big chunk will be what is called the central potentials. And in particular, the one that is called the hydrogen atom. Okay, so this is the menu for chapter 5. Now we are going to start with the material point in 3D. So, well, I'm going to focus on the x, so focus on the x representation. Of course, as usual, there is a p representation and so on, right? Etc. So again, this is like writing the vectors in a given basis, and obviously even in 3D you could write the vectors in different bases. For instance, you could write the vectors in that basis. But again, the techniques are essentially the same as we saw for 1D, so there's no point in me writing again all the formulas. It would be probably more confusing if I were to start all the formula again. It would give the impression that there's something really new. So, what is position in 3D? Well, this you know, right? I'm going to write the vector x. This is a kind of normal vector. Sometimes it's written like this, right? X, ex, plus y, ey, plus z, ez, with these the unit vectors in the different directions. And for convenience of some compact notation, sometimes I will write this thing like this: x1, e1, plus x2, e2, plus x3, e3. And the corresponding integration element, of course, is dx, would be d3x, would just be dx1, dx2, dx3. These are for the numbers. Now let's see what are the Hilbert space and operators. So the Hilbert space, well, guess what it is? Is the square integrable functions on R3. So the Hilbert space is denoted L2, this time of R3. Before it was L2 of R, and is defined, as you can expect, as the set of function psi from R3 to C, such that integral of psi of x square d3x is, well, is less than infinity, and then we normalize it later to be 1. A generic state will be written psi equal integral d3x psi of x x. And now I have to say something that I've not written, unfortunately, in the lecture notes. I upgrade them for next year. What is this object? Well, formally, if I were to work at the level of the cats, I would have to discuss a notion that I have not really introduced, that of tensor product. We have seen something in 6 quantum pieces. So this cat X is actually can be seen as a product, as a tensor product of 3 cats. Now, again, this notation is not familiar to you, so let me show to you how this looks like in wave function representation. So if I have any x0 vector, right? What is this? This we know is delta of x minus x0. But what is a delta function for vectors? Well, it means every component of the vector must be equal. Every component of the 2 vectors must be equal. And so these, and the dimension, the units is 1 over meter cube square root. So this is actually equal to delta x1 minus x0 component 1 times delta x2 minus x0 component 2 times delta x3 minus x0 component 3. So here, at the level of the wave function, you see very clearly there is a product structure between 3 wave functions. And if you want these, that I'm not going to use anymore in this course, would be the abstract vector version of this product structure. Okay? I'm going to use these only now just to show you what the position operator is. I need the eraser. Because the position operator is a kind of interesting, maybe I should say one thing. However, you see a generic function psi, maybe that's important at this point, a generic function psi is not going to be equal to psi of x1 times psi of x2 times psi of x3, clearly, right? You could imagine a function that is, for instance, if I take this function, 1 over x, something of that type, well, you know what this is, right? This is equal to 1 over square root of x1 square plus x2 square plus x3 square, and it's clearly not of that type. Right? So the product structure is here because of this delta behavior, but a generic state may not be what we call a product state. Okay, with these remarks, let me tell you what is the position operator now. I'm going to erase these. And also this remark that is kind of obvious. The position operator is going to be, well, again, what you expect, right? It's going to be one of these vector operators. So there is an operator for each component x1, x2, x3. So this will be in general sum over u equal 1, 2, 3, x of u, eu. Maybe this is a bit more intuitive meaning of this kind of vector operators, vector of operators, than the vector of Pauli matrices that we saw in the 2-level systems. But it's the same structure. Remember, we had sigma is equal to sigma x ex plus sigma y ey plus sigma z ez. It was also a vector of operators. However, here these are 2 by 2 matrices. These are going to be multiplicative operators. Okay, this is just a reminder. And what is this xu? Xu is, well, of course, this, right, is the integral over R3 d3x times multiplication by the youth component of the vector times x. But now, if you use the tensor product structure that I told you before, you see this integral here is dx1, dx2, dx3. Here there is only one of them, let's say x1, for the sake of it. And here there is again x1, x2, x3 in product. So x2 and x3 can be integrated out using the closure relation integral dxv xv is equal to 1. That's true for every component. If I apply these to the v component that's different from u, this would be equivalently equal to r dxu xu xu xu. And this is what we had for the, and okay, if you want tensor identity on v1 and v2 different from u, if you want the whole thing. Okay, so essentially it's and this is what you expect, right? This is the position operator in the uth direction u, and times nothing in directions in the two direction orthogonal to u. Okay, so barring a few mathematical things that the first time you see them, tensor products and whatever, essentially this is nothing else than what you expect, right? I really don't want to pretend that there's anything deep in these rather than the extension of what we did for 1D. What is the momentum operator? Let's do it in blue just because why not? The momentum operator is what you expect, sum over u, pu, eu, and what is pu? Pu is is this integral over R3, and then the derivative with respect to xu, and then x d3x, and again I could do the same trick as I did there and write it as something on xu times the identity on the others. And so in shorthand, the shorthand representation, textbook shorthand representation of this thing is that P is equal to minus I h bar gradient. This is the shorthand representation of what is written here. And again, nothing new, right? The momentum was the derivative, now the momentum becomes the gradient because it has 3 dimensions and is a vector. Okay, commutation relations between these two, and with this we finish the operators. I erase now the matrix elements. Commutation relations. Well, the commutation relations are like that. So first of all, two different components of the position operators always commute. Two different components of the momentum operators always commute. And the component of position with a component of momentum, they commute if they are different. If they are in orthogonal directions. And they don't commute in the usual way if they're in the same direction. So this is I h bar identity delta uv. Great. Here you have essentially everything you should know about the translation from 1D to 2D of the states and the operators. To 3D, sorry, of the states and the operators. And the dynamics, I'm going to write it just because for reference, right? But it's really kind of waste of time. So you can put me at a 1.5 or 2.0 speed for this part. There's really nothing to be learned that is not a repetition. So for the dynamics, the generalities, right, of the dynamics. Well, the Hamiltonian looks like this. In full generality. Now, this fellow is called a vector potential. So, first of all, this is the most general form of an Hamiltonian that respects Galilean invariance in 3D. Now, the interpretation of this object might be a little bit surprising. Somehow, where does it come from? Well, this comes usually if there is a magnetic field. This is called the vector potential. Of course, if it's a magnetic field, you would write this term as the electric charge times the vector potential. So there might be a constant here, but I mean, you see what I mean here is that there is an object of vectorial character that depends only on x. This would be the vector potential of the magnetic field that you should have seen in electromagnetism, right? Now, in all the examples that we are going to deal with in this class, we are not going to do the magnetic field. It's not too difficult. It's a typical thing that you do sometimes in QM1 if you have more time, or in QM2. So, but we're not going to do it. So, because of these, the Hamiltonians we are going to look at will be just absolutely the usual ones. So, p squared over 2m plus v of x. From this Hamiltonian, it follows that there is, of course, a continuity equation with a current. There's a continuity equation between rho of x, that is psi of x squared, and a current j of x, that is again the same thing as the other one with gradients instead of derivative. And again, I never know it by heart, also in 3D, is psi of x gradient psi star of x minus psi star of x gradient psi of x. And this is a vector. And the Ehrenfest theorem holds exactly like the one-dimensional one with vectorial objects, right? So we have that in the Heisenberg representation, the dx over dt will be p over m, and dp over dt will be minus the operator that is described by the gradient on v evaluated in x. So really the same. Why is the same? Well, because of the commutation relations of x and p, right? That essentially, because all the x and the p's commute when they are in orthogonal direction, you can essentially solve the differential equations in every direction and just sum them, right? So you have for each component, you have the normal one-dimensional Ehrenfest theorem. You just sum the three components and you get that, right? So there's really nothing particularly difficult. Okay, so with these, we cleared this. And now we go to the real topic for this lesson, that is angular momentum. So because I have not discussed symmetries, the angular momentum may come down a little bit from the blue. But I will tell you very quickly where it comes from. So the point is to look at rotations. So let's focus on rotations. Rotations of what? Well, of your coordinates. It can be a passive rotation. You keep your object fixed. Let me do it with a pen. And you rotate your coordinate axis. Or you can think of an active rotation in which you keep your axis fixed and you rotate your vector or your matrix or your scalar, whatever you want to do, right? So the question is, how do we describe rotations? So think of, maybe, I don't know, think of a quantum state, for instance, right? I choose some coordinates here, x, y, z, and as a consequence, I don't know, my wave function is psi of x, my spin is plus n, my Hamiltonian has some other structure, depends on my Hamiltonian may depend on the, let's say, the charge times the electric field in X, whatever, right? And now I talked to one of my colleagues that had the bad idea of taking a different system of axes. My colleague will have a psi of x prime, the spin will be in direction n prime, the Hamiltonian will be q of the field rotated in position x prime. I could put a prime here if you want, just to. So, and then the question is, what is the relation between these objects? Right? Obviously, we are describing the same physics, right? So I don't know. Let me just draw a vector there. That could be x. That could be the spin. That could be e. There's a vector here, and the vector is still there. The vector has not changed, but the representation of the vector has changed. Right? So the question is, how do I relate at the level of quantum objects my representation to her representation? We know how to do it for the x, right? For the x, it would be just a rotation. But how does a rotation apply on a state or on an operator? How would this change? Right? Okay. So, sorry, the Hamiltonian, of course, stupid mistake, the Hamiltonian is, of course, the electric field and then with the direction also. There, you see? People, when you're at the whiteboard, you make mistakes. This is good for your viva, you see? If I tell you, are you sure? You say, oh, no, I forgot something. You see, I can forgive you. So don't be worried for the viva. I also make mistakes when I am at the whiteboard and improvising something. Great. So now, now I will drop you something that you don't know and I didn't tell you. I mentioned just very quickly is that any symmetry, this is a symmetry, right? And there is the Wigner theorem that says that a symmetry in quantum mechanics, especially a continuous symmetry like a rotation, is associated with a unitary operator. So what that means is that, for instance, let's do it with a spin, right? That plus n prime, the new state that represents the direction n prime, there will be a unitary that describes that rotation. And that's how this state is related to my state. And of course, the same will be for a wave function, psi prime. There will be another, a unitary that relates to psi. Now, this unitary is 2 by 2. This unitary is infinite by infinite, or whatever you want to do. It is infinite dimensional, right? So they're not the same unitary, but they describe the same rotation. So that's getting a bit confused, right? How come? So there is one rotation that is described by different unitaries. Yes, because we're acting on systems of different dimensions. Okay, but both unitaries have the same structure because it's the same rotation. And this is, you have to believe me, that the form of that unitary is like that. U. Now, of a rotation, this is a rotation around the axis m by an angle alpha. The unitary is written like this: e to the minus I alpha n times j over h bar. M, sorry. So let me describe to you the objects of this construction. Alpha, we know, is the angle. M, we know, is the axis around which we rotate. What is J? J is angular momentum. This is called, something that appears there is called the generator of the symmetry, in this case of rotations. And this is what is going to change between the spin half. It will be a 2 by 2 matrix, so some Pauli matrix, we will see which ones, and an infinite dimensional system. These might take some time to digest, but please think calmly about this. So remember, it's the same rotation, that's why it's the same rotation, same alpha, same m, but we are applying this rotation to describe objects of different dimensionality. A vector 2 by 1, an infinite dimensional vector. Therefore, this matrix must have different dimensions. The difference is only in the way we represent angular momentum. And there is only one way to represent angular momentum for a spin half. There is one way to represent angular momentum for a spin 1, for a spin 3 halves, and for a material point. The angular momentum operator is always uniquely defined given the physical object. So we're going to see, so now you can go back to the plan. I try to explain to you this point. Now we are going to do the general theory of an angular momentum. What should an angular momentum satisfy to be an angular momentum? And later, given this general theory, we are going to construct two examples. One for the spin half, and one for the material point. Okay, great. So, where does the construction, okay, this is the construction I'm going to skip. The example is given in a tutorial, that is a tutorial, if I remember correctly, B3, or something like that, which means that I'm not going to ask you to, it's not something compulsory material for the module, but for those who want, you can practice what I'm going to tell you now in a tutorial. Tutorial number 1, I think, of chapter 5. Let me erase the rotations. I will also erase these. Well, maybe we can also erase the unitary for the time being, yes. No, let me just leave it here for a while. So, the definition J equal to J1 E1 plus J2 E2 plus J3 E3, alternatively again written Jx Ex plus Jy Ey plus Jz Ez, is an angular momentum if and only if the commutation relations are like that. J1 J2 is equal to I H bar J3, and of course plus circular permutations, which means J2 J3 is equal to I H bar J1, and J3 J1 is equal to I H bar J2. So this is the definition of angular momentum. If I ask you to check, is this operator, this family of operators, this vector operator an angular momentum, you check these. It was done in the exam last year, incidentally. You can check, I posted that in Luminous. Now, where does this come from? Why? Well, that's where, so the why, you check the tutorial. Tutorial 5.1, the idea is that these guys represent rotations. And so therefore, when you combine these unitary operators, you need to have the same algebra as the algebra of rotations. What does that mean? Example, right? If I do a rotation of 90 degrees around x, followed by a rotation of 90 degrees around z, and let's say I start from the vector z. Okay, so what happens? I start from z, I rotate around x, so I end up in y, this is the rotation of x, and I rotate 90 degrees around z, I end up in minus x. So this is minus x. Okay? If I were to do the opposite, if I were to do a rotation on first, oh sorry, this, I did it in the other way. If I were to do first the rotation around z, and then the rotation around x, what happens? Well, z rotating around z doesn't change, so this is z, and now I rotate again z around x, I would get y. So you see, okay, this is the famous case that the rotations do not commute. Right? And these unitary operators must do exactly the same. They are representing rotations. This is what is called, it's called that these unitary operators is a representation of the group of rotations. So they must obey the same algebra. And when you impose that they obey the same algebra, you find that this happens if and only if this J operator satisfies these commutation relations. I know it sounds a bit mysterious. If you really want to know, you do the tutorial. If you don't want to know and you just say, no, I'm already confused enough, I just trust this definition, you trust this definition, you just remember in the back of your mind that angular momentum is the generator of rotations. It means is related to rotations by a formula like that. Okay? Now what we're going to do is to take this definition seriously and to study this operator J in detail, again in general, for any J. This can be 2 by 2 matrices, 3 by 3 matrices, 4 by 4 matrices, or infinite dimensional objects. Okay, so what do we do here? Well, I mean, these operators do not commute, so obviously the JK do not commute. So they don't have a common diagonalization, a common set of eigenvectors. But oh, sorry, I should have said that these guys are Hermitian. Well, that means just the JK equal to JK dagger. That's another condition to be an angular momentum. But there is one thing they all commute with, and this is what is called J square. J square is just this operator. And this is you see, is a kind of, from the point of view of space, is a scalar operator, right? There's no more vector. So this is just a matrix constructed from those three matrices, taking the square and summing them. And now it's kind of easy to check that J square commutes with every GU. Okay, let's get the proof to that. Well, the proof is kind of boring, right? Let's do it for Jx. U equal x. What is this? Well, J square is this, so I can split the commutator. This is 0, fair enough, because it's the commutator of an operator with its square. And now here we have to use one of these formulas that, how does that go? I never remember these ones. So this guy is equal to, you remember this AB times commutator with C is equal to some stuff. Yeah, the formula is like that. I've written it here. AB commutator with C is equal to A commutator with BC plus AC commutator times B. So let's see, A times BC is JY commutator JY JX plus AC JY JX times B. The order is important because they may not commute. Right? This is exactly the same with the Z, right? So let me continue here, plus, so equal, plus JZ, JZ, JX, plus JZ, JX, JZ. Okay, now we apply our rule. JY, JX. Okay, JY, JX, it's here, reversed, so it's minus IH bar JZ. Yes, that's also minus IH bar JZ. And this is ZX. ZX is IH bar JY, IH bar JY, and now you see it's 0. Here I have JY, JZ with a minus sign, JY, JZ with a plus sign, JZ, JY with a minus sign, JZ, ZY with a minus sign, with a plus sign. So indeed, we prove that this is 0. And of course, by symmetry, would be the same for every other component. Okay. And now that I have done this, I can state the main result, and then we are going to prove it. This is one of these results you need to know by heart. So this is, let's call it even a theorem. The common diagonalization of J square, and typically we choose JZ as the companion one to diagonalize. Like the Pauli matrices, we have chosen sigma Z to be the diagonal one. Here also we are going to choose JZ as the one is typically diagonal, and then the others will not be diagonal, right? So is such that, so I'm going to characterize now eigenvalues and eigenvectors, especially eigenvalues. The eigenvalues of J squared are of the form and this is the one that you really need to remember, H bar square J plus 1 with J integer or half integer. It means the J can be 0, 1/2, 1, 3/2, 2, 5/2, blah, 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 blah. First statement. Second statement. For a given J of J square, the eigenvalues of Jz are of the form m times h bar, with m taking all, it means that the 2j plus 1 values defined like that, m can be equal to minus j plus 1, minus j plus 2, keep adding until you reach j minus 1 and j. And you can check if these guys are integer or half integer, the sequence is well defined, and there are indeed 2j plus 1 numbers. Okay, so in other words, maybe if I write it in an algebraic way, how do I write that? So it can be written like this, right? That J square, the common vector, well, there can be, if it's a pure state, there can be some other variables like the energy or something else, but let me just write it with these. Jm is equal to h bar square jj plus 1 jm, and then jz jm is equal to h bar m jm, with, again, j can only be integer or half integer, and if a given j is present, all the m are present. Of course, they define orthogonal eigenvectors. So, yeah. Okay, that's the theorem. And now I'm going to spend some time proving it. It's not too different from the proof of the harmonic oscillator that we did last week. In fact, it's quite similar. So what I'm going to do in red now is the proof of the theorem and see how we got there. In the lecture notes, this may be interesting to notice, I have written these vectors K, J, M. So here the point is the following. It might become clearer later. For a generic system, the properties of angular momentum do not explore the whole Hilbert space. So once you specify angular momentum, there may be still some things to clarify in order to have pure state. So if you only specify angular momentum, you could have angular momentum at different energies, for instance. You will see these in the hydrogen atom. Therefore, if I only tell you the angular momentum is, let's say, J equal 1, M equals 0, you still don't know, yeah, but what is the energy? Right? The energy levels for an atom behave more or less like these. We're going to see it in the hydrogen atom. Therefore, I wrote for convenience, if I want a pure state, something that is perfectly maximally defined, I may have to add some other information. In my example, the energy. So this K, you can, for the moment, for the sake of the angular momentum, we can essentially ignore it. It's just in order to be rigorous in my notation, that if I just write Jm, in general, this may not be a pure state. Because again, there may be degeneracy in other values that I'm not telling you about. When it comes to spin half, that's the whole thing. But when it comes to angular momentum, there is something else. Now, for the sake of the proof, I will omit the K, just because, well, it's just bothersome to write it. Okay, keep in mind just this remark. Okay, so, well, exactly, so the proof. First of all, exactly like the harmonic oscillator, we see that the eigenvalues, so first point, the eigenvalues of J square are non-negative. Well, it's kind of written there, right? Well, that's the same proof as we had in the test, J square psi. Well, it's the sum of these terms, and you recognize in each term these plus these plus that. Okay, so this is certainly non-negative. Okay, that's fine. Now, then there is a kind of convenient observation, convenient in view of the result. Of course, the first guy who did this diagonalization didn't know about that. And once he found the result, they realized, hey, maybe there's a very compact way of writing it. So every non-negative number lambda can be written lambda equal j plus 1 with j positive. Proof? Well, proof, solve the equation j square plus j minus lambda equals 0, and there are always solutions. So they just okay, so that's what we're going to so because of this, I just erase this convenient observation. You keep it in mind, it's in the lecture notes. So let's write, because of this, let's write what we have written already there. J square Jm is equal to, H bar is for dimensional reasons. Jm. So here, again, because of the convenient observation I just made, what I've written here is just that the eigenvalues of this operator is non-negative. And then I multiply by h bar square for, again, for dimension unit reasons, but, well, it's just a scaling, right? And then Jz on Jm, I call it like this, h bar m Jm, and I have no clue what m is at this point, right? I have no clue also what j is at this point. I just know that this is a positive number. So I know that j will be non-negative because that thing must be non-negative. That's all I know, but it's just a notation. Okay, so what do we do? Well, just as we did for the harmonic oscillator, we need to introduce something like creation and deletion operators. They were not exactly that, but something similar. So let me define j plus minus as the following non-adjoint operators. And we have, you can check, I think it's in a tutorial. Well, check. These things are going to be useful. J minus, the product of these two is equal to j square minus jz square minus h bar jz, and j plus j minus is equal to j square minus jz square plus h bar jz. In particular, then these two do not commute, the commutator being 2 h bar jz. Okay, this you can check. It's done in the lecture notes. You do it as a personal exercise if you want. Again, it's a matter of using those commutators of x, of jx, jy, jz. So now I have everything there, so I can erase this part. And now I have my usual lemmas that can be useful. So lemma number 1. So let me just draw a line here. Just, is that the values j and m satisfy minus j. So m is strictly, this m that I define here is strictly comprised between plus j and minus j. The proof is an interesting, complicated thing. So if I do the vector j plus on jm squared, this is this jm j minus j plus. So the j minus is the adjoint of j plus jm. These you look at here, and now we have all the numbers, right? Because with j square we have, jz square we have, and jz we have. So what is it? It is h bar square j plus 1 for this, minus h bar square m square for this, minus h bar square m for that. And you can check that this guy, it's written like h bar squared j minus m j plus m plus 1. Okay, similar calculation, j minus on jm, exactly the same thing. I'm not going to do it here, and you end up with h bar square j plus m j minus m plus 1. Now, let's see if I can convince you that so, of course, this must be positive, both of them, because it's a square of a vector, right? So, this one being positive implies what? Let's put it on the axis of M. I'll do it in a different color. The first term being positive means that M must be smaller than J, but must be bigger than minus J minus 1. So these are the possible values of M for condition 1. In condition 2, this tells us that J must be larger than minus M, sorry, M must be larger than minus J, and must be smaller than J plus 1. So these are the possible values of M according to equation 2. Both equations must be satisfied. Sorry, I didn't write what the equation 2 is. It's this. Both equations must be satisfied, therefore M can only be between minus J and J. Okay, this proves the first lemma. I can erase the proof. We proved it. Lemma number 2. Okay, this is the one where we have the kind of creation alienation operator, right? Lemma 2. This says that there are two parts. If M is equal to minus J, then J minus applied to Jm equal to minus J is the vector 0. If M is strictly larger than minus J, J minus Jm is proportional to Jm minus 1. So this is similar to the annihilation operator, right? This J minus thing is such that it removes one excitation from M. M goes to M minus 1, and if it's already at the bottom, it will kill the vector completely. Okay, proof. Well, if you look at, oh, I erased it. So I had a condition that I just erased, sorry for that. So we had these was equal to h bar square, j plus m, j minus m plus 1. And now these can only be 0. So if m is equal to minus j, this is 0. And the only possibility for the norm of a vector to be 0 is that the vector itself is 0. So this one we proved. And now the other one, you just use the commutator, well, which is another commutator that so j square j minus is equal to 0 because j square commutes with jx and jy. So therefore, j square on j minus jm, it commutes, is j minus j square on jm, but these, by definition, is h bar square j plus 1 jm, so the whole thing is h bar square j plus 1 j minus times jm, and so we have that j minus remains an j minus jm remains an eigenvector of j square for the same eigenvalue. Okay, so the fact that this, now we prove that the j is unchanged, and now we need to prove that the m goes down by 1, and this comes from something that I again have not proved, but you can prove it trivially, that jz j minus is equal to minus h bar j minus. The motions are exactly the same as the ones for the harmonic oscillator. if you want in detail, you have in the lecture notes, and this proves that the trick is the same, right? Jz J minus on Jm will be equal to, you do this, you remove one J minus, so essentially you get H bar M minus 1 J minus Jm. Here, I can let you figure it out. It's done explicitly in the lecture notes anyway. And so again, this concludes the proof that this vector is an eigenvector of Jz for the eigenvalue minus 1, M minus 1. Good, so we've done that. Then we have the third lemma, which is, of course, exactly the opposite with J plus, and I will not bother proving it. It's absolutely the same type of algebra. We have seen it already many times, and it's just boring. So the lemma number 3 is that if M is already equal to J plus J, M being equal to plus J is 0, and if M is strictly smaller than J, J plus Jm is proportional to Jm plus 1. Right? So there's a slight difference with the harmonic oscillator. In the harmonic oscillator, when you create an excitation, you can create as many as you want. It's unbounded from above. Here, once you've created that at most, M takes at most the value J, so when you've created J excitation, you can create one more, so there is also this 0 here. And the last point to conclude the proof is really exactly the same argument I did for the harmonic oscillator, namely that if this value were not integers or half integers, by doing this ladder, you would at some point exceed you would find formally you would find a non-trivial eigenvector for an eigenvalue that does not exist. Right? Exactly the same as the harmonic oscillator, and the fact it's bounded from the two sides gives this possibility of half integer. You can do it by yourself. So with this, we finish the proof of that famous theorem. And there are some calculations in the tutorial, like you use things to get some other results. Okay. Last point of this lecture is, before going to the examples, is what is called something like, is a very important consequence, actually is one of the reasons why we introduce all this mess, is invariance by rotation and what is called essential degeneracy. So this, with this we finish this general part. So let's see. So these are kind of two remarks, two consequences. So point one is that a physical quantity A is invariant by rotation if and only if A commutes with the whole of angular momentum. Well, so this thing means really that A Jx is equal to A Jy is equal to A Jz is equal to 0. And the proof is a kind of thing. So what does it mean invariant by rotation? Invariant by rotation means that if I do any rotation, E minus alpha M J over H bar A E I alpha M J over H bar. Remember, A is a kind of a matrix in Hilbert space. Therefore, you remember for real matrices, if you have a matrix, a rotation is given by these, right? So similarly here in Hilbert space, if I have a matrix, the rotation is not U times A, but is U times A times U minus 1. Okay, that's what I've written here. And if a quantity is invariant by rotation, it means that this is equal to A for all alpha and for all m. And, well, you see for the theorem of a function of an operator that whatever this direction is, right, if A commutes with J, then I can move this operator here, this becomes the identity, and then that's it. Okay. By the way, if these were the Hamiltonian, then Hamiltonian is invariant by rotation if and only if the angular momentum is conserved, which is so under the dynamics, right? The angular momentum does not change with time. So if they so h j equals 0 would imply that j in time is equal to j at time equals 0 in the Heisenberg representation, and we know that for the angular momentum this is the case if the Hamiltonian is invariant by rotation, right? So so this is if and only if. As an example, we are going to use this theorem at some point. The second remark is actually a theorem that is a strange theorem, but it will have a lot of importance, what is called the essential degeneracy. So if A is invariant by rotation, its eigenvalues are degenerate for M, or let's say independent of M, M being the eigenvalue of Jz. The proof, so okay, proof, right? So A is invariant by rotation, therefore in particular AJZ is equal to 0, and so we have a base of common eigenvectors. Let me denote them by AM. Actually, I could even put AJM for every single J, right? And now, so let's assume that the eigenvalues of A actually depend, so that A, J, M, it has a value here, A, this A here, maybe, okay, let me maybe not call it A, I will call it K as I did before. And let's assume the eigenvalue of A depends on K and on M. I can even remove the J. Km. So K can contain M. So let's do it like that as I did in the lecture notes. Let's assume that this depends on M. Then what I can do is, well, I can apply, for instance, which one I choose? The J plus. Okay. So so let's assume, for the sake of the argument, that M is strictly smaller than J. Then what do I have? I have that J plus on Km, well, this is going to be something that is a Km plus 1. Okay? But J commutes with A. J plus commutes with A by assumption of invariant by rotation. So here, you see, I've used here that A commutes with Jz. Now I'm going to use the fact that A commutes with Jx and Jy also. To reach my conclusion, right? So I need really that it commutes with the 3 components. So now I can do this. So now, of course, J plus on A Km. What is this? Well, this is this. So it's A Km J plus on Km. And so, but this commutes. So this would be actually A on J plus Km, and this is something like Km plus 1. And since I'm in a basis of eigenvectors of A, then this would be something proportional to Akm plus 1 of K of J plus Km. So you see that here we have two equations. Here, by applying A first, we took out the eigenvalue and it depends on M. And here, by using J plus first, but then remember that this is still an eigenvector of A, we took out the A and depends on M plus 1. So therefore, but these two numbers should be equal. Therefore, M and A, the eigenvalue of A cannot depend on M. And of course, if you were to do the M equal J case, of course this doesn't work, but you can just do it J minus, and you get exactly the same result. So this is important, that if an operator is invariant by rotation, it has degenerate eigenvalues, and the degeneracy are related to the value of Jz. Okay, so we can finish here this lesson if the technicians remember, can see my message. Let's wait a few seconds. If he doesn't see my messages, then we continue directly with the next lesson. Otherwise, we'll stop here. Unfortunately, we've not been able to install the facility to stop by myself, so I have to ask someone. Okay, he doesn't seem to see it, so I tell him don't stop, and we continue. Good, so what have we done? This will be a long video, but of course you feel free to stop the video at this point and then take a rest and then whatever, and then we move to the next part. We have done these, the generalities. Now I'm going to do these. I'm going to do the two examples of the angular momenta. The one for spin half and the orbital angular momentum. Okay, so spin half. What does that mean? Well, we are going to explore what happens if J, this J that I just wrote, the small j, the eigenvalue, is equal to 1/2. So what is a spin? First of all, generic spin. It's a magnetic moment, M, but associated to it there is an angular momentum, S, such that the relation is M is equal to gamma times S. This guy is called the gyromagnetic factor. So this S is what I called J before. It is in every single textbook, so we have to adapt to this, that when you do the general theory of angular momentum, you call it J. When you do an example that is specifically a spin, you call it S. And when you do the angular momentum, the orbital angular momentum for material point, you call it L. Okay? So, well, S, L, and J have the same properties. It's just now to remember that this is an angular momentum of spin. Okay, so let's see what happens. So I'm going to construct the spin half from scratch, and you will see what comes out, right? It comes out the spin half we studied in chapter 3. But I'm going to start really from the recipe of this chapter, okay? So what is SZ? Well, SZ, so I'm assuming J equal to 1/2. Sz is an operator that has two eigenvectors. This one has eigenvalue, remember, h bar times m, h bar over 2, and m minus h bar over 2. Right? If I were to choose these as a basis, so if I were to choose that 1/2 plus 1/2 is represented at 1, 0, and 1/2 minus 1/2 is represented at 0, 1, well, this operator, Sz, is h bar over 2, 1, 0, 0, minus 1, which is h bar over 2 sigma z. I hope you like it, and I hope also nobody is surprised to find that the angular momentum of a spin half in the z direction is essentially sigma z, and now you understand why it's called a spin half. There is this h bar for dimensional reasons, and then there is 1/2 there. All right? Okay. Now, how do we find I think everybody guesses now what are sigma Sx and Sy, but let's suppose we have never seen Pauli matrices, and let's rederive it. So I will need a formula that I didn't write before because it's a bit xiong. So let me write it here now, because this one is useful. Where do I write it? Well, my pedagogical thing here is getting a bit boring, so I will just write it here because it's kind of useful. You remember that what you have left to do is the central potentials. There was a formula that you can prove, I think it's done in some tutorial, is that J plus on Jm is a very strange thing. It's this, is h bar square root of J plus 1 minus m plus or minus 1. This plus or minus refers to this plus or minus. And then we know what happens. J remains the same, and then m increases or decreases by 1. So this formula, I'm going to use it now to find Sx and Sy. So let's see what we have there. What is this? Here, just that I don't get confused. So what do we have? S plus of 1/2 plus 1/2. Well, plus 1/2 is already the maximum, and we're trying to apply S plus. So this is going to be killed. S minus on 1/2 plus 1/2. Well, this is going to go something that is something of this type. We're going to lower by 1, but there's a coefficient in front. The coefficient is given there. Let's see if we're able to compute it. Okay, we get 1/2 here. 1/2 plus 1 is 3/2. Minus m. M was plus 1/2. And we are applying the minus operator. So it's 1/2 minus 1 minus 1/2. What is this? This is 3/4. And this is plus 1/4. So it's equal to 1. Well, h bar. And if I do on the other basis vector, so S plus of 1/2 plus 1/2, sorry, S of minus, okay, F plus minus 1/2, these, well, you can check that it's exactly the same. And then, of course, S minus of minus 1/2 is 0. Okay? And now, using that S plus minus is equal to Sx plus I Sy, you plug these things in, and you find that Sx is equal to h bar over 2 sigma x, and Sy is equal to h bar over 2 sigma y. Just do it for the sake of... And so therefore, what we have found through this complicated construction is that the angular momentum for a spin half is h bar over 2 times the vector of Pauli matrices. Okay, now, in the tutorial, what is this? Tutorial 5.3, the same construction for j equal 1. For those who are interested in doing the same exercise with 3 by 3 matrices and to find out what are the analog of the Pauli matrices, how the spin looks like for j equal 1, you can do that tutorial. And now I have something funny to tell you here. This is a bit of physics. What is the unitary operator that describes a rotation? Okay, so then of course it's, remember the general recipe is e to the minus I a m j over h bar. So now if I put, instead of j I put my s, I get e to the minus I alpha m times sigma over 2. Here you see it appears one of these m times sigma operators that we practiced in chapter 3. And this is a rotation by angle alpha around the axis m. And if you open it up, I think this is done in a tutorial, you get that this is actually equal, there's a compact formula here, cos alpha over 2 identity minus I sin alpha over 2 m times sigma. That's the matrix that it is. So, well, it's not particularly funny. Well, what is funny is what happens. So, okay, this is general and it's very important, used all the time and all the things. Now, let me show you what happens if I take alpha equal 2 pi. Right? A rotation of 2 pi should not change anything. Because, indeed, it doesn't. Let's try to do that. If I plug alpha over 2 pi here, what do I get here? I got cos pi times 1, so it's minus 1. And then sin pi times this, so 0. I may say, well, indeed, for every axis, a rotation by 2 pi is the identity. Oh, there's a minus sign here. Well, is it important? Let's see it. First of all, let me show, one thing that is obvious is that if we do alpha 4 pi, then I get 1. So this thing, the fact that you have to do 4 pi in order to get rid of that sign has a name. It's called 4 pi symmetry of the spinor, where spinor means state of a qubit, state of a spin half. So this is the name you find in the literature. But now let me elaborate a little bit. This is not done in detail in the lecture notes, so I will do it here. It's a bit of physics, not mathematics. Is this a physical effect or is just well, whatever? Some mathematical incident that happened. Okay, let's try. So, well, if I do a global rotation, okay, for instance, a passive one. This is the case I was telling you before, right? I go from here to here. The whole space rotates, right? Then what happens? Every state, but by 2 pi, right? So then every state, sorry, let's do the states with for qubits. Every state plus n goes into u time plus n, and u is this, minus plus n. This is a global phase. So we can get rid of it, it doesn't matter. So, okay, thanks God, if I do really a rotation of my whole space by 2 pi, the physics doesn't change. Okay. Now, however, what happens if I do a active rotation, active and partial rotation? Let me go for an example. What I mean by partial, I mean I do a rotation on a spin only when it is somewhere. And now we are going to see something that is beautiful. Let's go back to our beloved Mach-Zehnder interferometer we had in a tutorial. Okay, so if you remember correctly, if the path has same length, the probability was 100% here and 0% here, if I come in from there. Now let's suppose that the particle that is traveling through this interferometer has actually a spin. Okay, so the spin is in direction plus n here. It goes here. Here the beam split doesn't change the spin, so the spin is still plus n. No problem, right? The particle keep going. But the spin is a magnetic moment. I could put a magnetic field here, in that part of space, B. And let's assume that this B corresponds to a rotation of the spin of 2 pi. Okay? This magnetic field, a magnetic moment precesses in a magnetic field. And let's assume that the intensity of the field times the time the particle spends in that region is exactly what is needed in order to do a rotation of 2 pi of this type. So now what has happened? Well, what has happened is that the state of this particle here, it is still plus n, and here it is minus plus n. You see, it's no longer a global phase because it affects only this part of the wave function, not that part. Of course, this can only be done if there is more than the spin, right? Here there is the spin and the spatial degree of freedom that is the particle propagating in the interferometer. So this is, it's exactly the same. So you see that the wave function, the total state is essentially the same, but this component has a minus sign. This is exactly the same as I have done nothing to the spin, but I have added a delay on this line that would lead now to destructive interference on this path and constructive of the other. This experiment has been done in 1975 by the group of Helmut Rauch with neutrons. And since then it has been done many times in any, and you have the reference in the lecture notes for those who want to read the article. So, in other words, this minus sign is a physical effect when it is a relative phase. You can really see it. If you were to put 4 pi, then this file disappears, and then we're back to 100% here, 0% there. And you see, so here, the Bloch vector has come back to the same position, but the quantum state has acquired a phase of minus that does not matter if it's a global phase, if I'm just induced by, for instance, a localized magnetic field. So this 4 pi symmetry of the spinor is a really physical effect that may or may not manifest itself depending on which situation we are looking at. Great. And now the last part of this lecture is going to be a bit heavy again. So if you want to take a break, please do it. Let's see. We are going to do now the orbital angular momentum. this is the angular momentum of the material point, which is called orbital angular momentum, and is this object L equal to X vector product P. So in other words, L component K is equal to, how do you write this? Component J, JKL, X component K, P component L. But this is the usual fully antisymmetric tensor, right? Where this is +1 if JKL is a permutation, even permutation of 1, 2, 3, is -1 if JKL is an odd permutation of 1, 2, 3, and is 0 otherwise. Okay, so now there is a way to prove that this is actually the generator of rotations for a material point, and this is done in a tutorial, again one of these optional ones, very instructive, a little bit heavy maybe in the manipulations, not entirely obvious in the manipulations, so not compulsory for the exam, but very instructive. Here we're just going to prove that it's indeed an angular momentum. So let's check what we have to do. We have to check the commutation relations. So L is indeed angular momentum. Let's try. Lx, Ly. Well, let's not fear that. What is this? That is x2p3 minus x3p2 Lx, and Ly is probably x3p1 minus x1p3. Okay, there are 4 terms. I will do it calmly because sometimes students are a bit confused here. This and this, not that, minus x1p3, sorry, x2p3, x1p3, then these, minus x3p2, x3p1, plus x3p2, x1p3. Okay, so what is this? Well, here we have x1 and x2 commute. They commute with p3, and p3 commute with itself. All these guys commute. This is 0. Similarly here, p2 commutes with everything else. x3 commutes with itself, so this is 0. These ones are not trivial, however, because we have x3 and p3. They do not commute. So let's see what these guys are. Well, let's write it up. This is x2 p3 x3 p1 minus x3 p1 x2 p3, and the second one is plus x3 p2 x1 p3 minus x1 p3 x3 p2. Now, those that commute, I can bring them out. I can bring them forth. This one commutes with this. I can bring it here. These also commute, and they also commute among each other. So this line is equal to, you can write it like this, x2 p1, and then what we have, p3 x3 minus x3 p3, p3 x3, and this line is equal to the same thing. I can bring this one out. So p2 x1, and then I have x3 p3, and so you see I can put them together, and I can have so this is equal the sum of these two, right? There's a sum here. This is equal to well, I can write it like this. For instance, I can write it as P2 x1 minus x2 P1 in factor of commutator x3 P3, and yes, sorry, I've made somewhere I've made some strange mistake. I don't know what I'm doing here. I copied something wrongly, probably. No, sorry, it's correct. This one is IH bar. And so what is this? This is IH bar x1 P2 minus x2 P1. They commute, I can do whatever I want. And this is, not surprisingly, LZ. So we have proved that Lx, Ly commutator is equal to IH bar LZ. This proves it. If someone does not believe that this is correct also for the other permutation, you can just check it. So indeed, this is an angular momentum. And now you can ask, well, these are operators on a three-dimensional wave function. So what are these kind of operators? Here it's getting nasty. I have to warn you, there's no way out. Here it's going to be a little bit of special functions and spherical coordinates and all these. But you can't escape spherical coordinates if you're trying to do rotations, right? It doesn't sound to be a stupid statement to make. So, I will try to give you mostly the gist of it. Now, some calculations I will skip. They are just boring. They can be found in any textbook. They can be done by yourself. It's really not my point now to try to redo this calculation on the whiteboard. But so what we want to find now is what are these operators and what are these. So question: what are J and M for L square and LZ. And because it's L square, we don't call it J, we call it L. But it's the same as the J. Okay. So, what we have to do is to work in spherical coordinates. So we are going to write a state psi. Remember that psi is written like this, right? Integral d3x psi of x, x. Now what I'm going to say, it's maybe too complicated at start, but it's a very important remark. You see, in X representation, these are just numbers. These are, well, these are vector, but I mean, okay, these are vector that whatever I write here doesn't matter. And this is a normal vector in R3. This is the usual integration element. So at this stage, even if I didn't define the corresponding operators, I can do a change of variables, just as you did in calculus, and write this thing as follows. R square sin theta dr d theta d phi, spherical coordinates. I can write the wave function with the coordinates r theta phi. And because it doesn't matter what I write in the ket, I can just also write in the ket the spherical coordinates. Anyway, it really doesn't matter what you write in the ket. Remember, the ket is just to keep track of the thing. So this represents a particle at position x. This represents a particle at the same position x written in a different way. And what I've done here is really the same change of variables that you have done in calculus. There's nothing mysterious here. Now, what will be very complicated, and we don't do it, nobody does it, is to define the operator corresponding to the angular variable phi. You have seen in a tutorial chapter 4 that that can get nasty, and even this one would be even worse, the azimuthal angle. But as long as I do the change of variables in the integral, it's just calculus. I can do that. If I do this, then, now I'll do it with some colors. The component Lu of the angular momentum acting here I don't know how to write it, let me skip that. And here it will act as a differential operator here. So this is important that this guy is also included in the differential, so I will put it here, Lu, right? And what is this small Lu? Or if you want, another notation for this would be Lu in the X representation. This is what you find normally in textbooks. And you can trust me that this is like that. Lx is a nasty thing, IH bar, sin phi d over d theta plus cos phi over tangent theta d over d phi. Ly is something, of course, similar because there's not much reason to find an asymmetry between x and y apart from the fact that maybe some things can change in phi. And then Lz is the simplest one. We're going to use it at some point. D over d phi, sorry. So actually, because they don't depend on R, I could have put my Lu here. But it's important that Lu can act also on this sin theta, right? That doesn't, you don't leave this one out when you do differentiation. Well, okay, and given these, it's again a matter of math to find that the corresponding differential operator L square is something like that. I don't pretend anybody to know these things by heart. Actually, probably I will never test these specific things in any exam. It's just for you to see that these things can be written down. Maybe the most important remark is that none of these acts on the coordinate R. These are properly, it's not absurd, right? We're talking of rotations. So the R coordinate is the radial one. It's normal that in a rotation, but that one doesn't get touched, and all that we change is the definition of the angles. And okay, now because of these, so we can write the eigenstates for L and M as, we can separate out the variable R, and then we can have some object here that for historical reasons they are written like this. Okay, because these operators don't depend on R, we can just take out the R, and then everything depends on theta and phi. We put it in these, let's say, eigenstates. And now we are going to see what these eigenstates are. This guy, we don't know. Huh? There's nothing we can say when we look at only at angular momentum. There's nothing we can say about the radial part. The radial part will have to be determined if it's an eigenstate of an energy, or if it's not an eigenstate, if it's a propagating thing. But now what we're looking for is the eigenstates of the angular momentum. So we're going to look at the properties of these guys here. And now, okay, this is a kind of heavy algebra, but I will sketch it for you because it's really traditional material. So what do we do? Lz Lz we saw before that was minus I of h bar d over d phi. So let's try the eigenequation, right? Minus I h bar d over d phi y L m theta phi is equal to what? Well, we want Lz on d is equal to h bar m on the same thing. Okay, but that's again one of these things that we know very well, right? We can remove the h bar, remove the h bar. This is a function of phi now. We're looking at it as a function of phi. And the equation is again derivative equal to a constant. So therefore, we know that YLM of theta and phi as a function of phi is kind of trivial. It is e to the im phi, and then there is a function of theta that we have to find. Okay, so we got rid of the phi dependence. The phi dependence is essentially trivial. But there's still something we have to do. Just as in the tutorial of chapter 4 about angular variables, the wave function must be single valued. So YLM of theta and phi should be equal to YLM of theta and phi plus 2 pi. Right? Because it's the same point. Even if the coordinate seems to have evolved by 2 pi, we are back at the same physical point. The wave function must have the same value. But this periodicity is only ensured. This implies that m is an integer. It might be all integers, it might be some integers, we have to check still that. The fact that m is an integer implies immediately, by the theory of angular momentum in general, that L is an integer. Because remember that the value of m will be minus L plus 1, and so on, L minus 1, L. So if these numbers must be integer, clearly L must also be an integer. So the non-trivial statement is that it cannot be half integer. So it's a property of the orbital angular momentum that we don't have any behavior like a spin half, where the angular momentum would be 1/2 or 3/2 or these kind of things. Maybe there are some limitations again. Actually, we're going to see that there's not. Every integer is possible. We have not proved it yet. But certainly the half integer values cannot be part of the eigenvalues of an orbital angular momentum. Okay, how do you prove that? Now that, so what we'll have to prove is to solve this guy for L and to prove that all the integers are possible. And you know what? Probably I will do it quickly. So, how do you do that? So left, find the FLM on theta and prove that every L, natural, right? Because L must be positive, is possible for the orbital angular momentum. Okay, how do you do this? Well, again, there is some. The argument is done in the lecture notes, and I think it's done clearly enough. So it's again one of these things where you start from L plus on LM, is equal to 0. It's similar to what we did for the harmonic oscillator to find the ground state, right? Remember there, we started from the idea that the ground state of the harmonic oscillator was an eigenvector of the annihilation operator for the eigenvalue 0, and this transformed the differential equation that gave the Gaussian. Similar, this equation here will give us the, this for m equal to L. Similarly, if we start from the highest m and we try to go above, this is going to be killed. So this is a differential equation. L plus is something like this. L plus is something like h bar e to the I phi d over d theta plus I cotangent theta d over d phi. So you apply this on your equation, now you do L plus on your function that is E I m phi f L equal m of theta. This is a differential operator, it gives something, and then this should be equal to 0. It gives, and you solve that, fully done in the lecture notes. I think it will be very boring if I do it now at the whiteboard. It gives you the f of theta to be equal to, where is this guy? Sorry, I messed up the indices. That's what happens when you're tired. Is m equal L here. The FLL of theta, and this gives some constant times sin theta to the power L. And after that, again, as we did for the harmonic oscillator, to find the L for m smaller than L, you just apply L minus a few times to that guy, and you see what happens. The result is not nice to write, but I will write the result in a compact form, just for you to see what it is. So this is the final result. All the details are done in the lecture notes. I just sketched for you what people do here. This is never something I'm going to ask you to repeat. Okay? By now you've understood that my exam will not be redo the proof of page 46 of the lecture notes about proving that the eigenstates of orbital angular momentum are like that. This is not going to happen. So, but the result is important to know. The final thing is this. So the L, never remember in which order you go, theta is found to be something that looks like that. Okay, I will write the obscene formula, then I will comment about it. Okay, so these guys are called the spherical harmonics. And have been found far before quantum mechanics by some French mathematicians who were studying systems with spherical symmetry. So, let's see what it is. This is just a normalization constant. So, for the purpose of the function, you can forget about it. It's just the number that normalizes this thing. This one, we have seen it before. That's the one that gives Lz on Lm is equal to h bar m Lm. The function, that's the dependence on phi. And that's the dependence on theta. The dependence of theta is a polynomial, and it's what is called the associated polynomial, sorry, associated function to a Legendre polynomial. And if you want to know what they look like, the first few ones are written in the lecture notes. The other ones are written in your favorite mathematics website or table of integral and special functions and whatever. So you just read them, right? I can just write what the first one is. Well, I mean, you find it. So if I write the first examples of spherical harmonics are not too difficult to write down. The first one is the only one I remember by heart. So this is a function of angular momentum 0. There are not many functions of angular momentum 0. It means it's completely invariant by rotation. It cannot depend on any angle. What can it be? A constant. What constant? Its square must be such that integrated over the sphere gives 4 pi. So this is 1 over square root of 4 pi. Sorry, yeah, what I mean is that this must be equal to 1. Sorry for the mistake. So this being a constant, it can go out of the integral. And then the integral of this thing is 4 pi, right? That's why I got this thing. And then the other ones are like cosine and sine. So the one with m equals 0, so if I have the m equals 0, L equal 1, this is something like cos theta, and those of m equal plus or minus 1 are sin theta, essentially. Well, for convention, there are some global signs here, and then sin theta, and then there is, of course, plus or minus here, plus or minus I phi, this term. Okay, well, and that's the other ones become more complicated. So these things are used all the time later in atomic physics, in physical chemistry. The famous orbitals that you have studied maybe in chemistry are linear combinations of these functions. This gives you an idea how they look like. But for this chapter, we stop here. And now the only thing that is left to do will be to do the central potentials and the hydrogen atom.